Okay, so since the variable's on the bottom, you have to switch this and then put a negative out in front.
Well, maybe.
Okay, and then what do you do from there? Plug in the 1 minus 3x everywhere you see a variable. And then what do you have to multiply that by?
3.
Negative 3, because the derivative of 1 minus 3x is negative 3. What?
That's okay.
Sure, that's fine, but these negatives will cancel and you can go. All right, no big deal. All right, and then number 18.
Hi, my name is Juan.
You got 1 over x squared, but my old eyes can't see that.
Yes. You're not that old.
Ancient.
What year were you born?
Old as the hills.
What year were
The same year as Philip Seymour Hoffman.
He's dead at all.
Yeah.
48.
So,
Spider-Man.
kind of creepy for me when people my age start dying. Okay, so again, the variable's on the bottom.
you? Yeah, but he also overdosed.
Jack, you
It's not like he died.
The overdose on here.
Yeah, we had a week like that filming too.
So I really have
I
been
know.
trying to manage my
Way to
heroin.
go. Like, how selfish. I know.
Okay, so you flip it over again because the variable's on the bottom, right?
Right.
And then plug that in for the variable. So it's negative sine cubed of 1 over x squared times the derivative of 1 over x squared. So we have to rewrite this as x to the negative 2. So the derivative will be negative 2x to the negative third. So if you want to neaten that up a little bit,
No.
then it would be sine cubed of 1 over x squared plus 2 sine cubed of that over x cubed.
I did it right, so I'm really happy.
Yay! All right, pass this forward, please.
And now we're
I don't
done.
know why I circled them.
And it for today.
Oh, it's not good for the day. There are 3 people, 4 people.
But the ratio.
The
It's all
percent?
about the ratio.
Is that what you're trying to tell me?
Those are the people that ask questions.
And Pua,
Percent?
he's gonna be so sad when she comes back. And Pua. Okay. Do you want her to be 8?
All right, so this is the super useful part now for how we will actually use these to solve problems. So this is the fundamental theorem of calculus, part 2.
Should I write this down?
Okay. Yeah, this is the good one to write down. This bit right here.
On my note card? Is it that
No, because you're going to use it so much that you're going to not need to write it down because you'll just know it, but you should have it in your notes. So if you are going to now do the integral from one number to another number of a certain function, this is a dx, not a 2, then what it is it's the antiderivative of the top number minus the antiderivative of the bottom.
That's it.
Yep. Yep. So that's how you solve
That's
these.
what they get.
Right. Big F is any antiderivative of F. Yep. So that is the big magic secret to solving integrals. Yeah. Right, and that's why it says any antiderivative, and funny that you should mention that because the book specifically points that out and says since we can use any antiderivative, we're going to use the simplest one. So for example, if you are trying to do something with x squared, the simplest antiderivative of x squared is x cubed over 3, so that's the one we're going to go with. Instead of this plus 4 or plus c. Yeah, so antiderivatives, your new best friend. Does anybody care about the proof as to why that
No.
works? Not so much? Okay.
Unless it's going to be on the 8%.
Yeah, probably not. Okay, so part 2 of the fundamental theorem states that if we know an antiderivative of f, then we can evaluate the integral simply by subtracting the values of f at the endpoints of the integral. It is very surprising that the integral from a to b of f of x dx, which was defined by a complicated procedure involving all of the values of f of x from a to b, can be found by knowing the values of f of x at only 2 points, a and b. Isn't that surprising?
Though,
Yeah, right,
That's the
exactly.
worst two
And
days
it
of my
is
life.
surprising,
Yeah.
but it's not as beautiful as.
Although the theorem may be surprising at first glance, it becomes plausible if we interpret it in physical terms. And we talked about this yesterday. If v of t is the velocity of an object and s of t is the position at time t, then we talked about before that if you take the derivative of the position, you get the velocity. And so that means that s is an antiderivative of v. In section 5.1, we considered an object that always moves in the positive direction and made the guess that the area under the velocity curve is equal to the distance traveled. So we've seen it in a real world context. You guys just didn't notice it at the time. All right? So let's do a real one. So let's evaluate the integral from -2 to 1 of x cubed dx. This is your new life.
I don't know, it's like the rest of this class.
Yes. So the rest of this class is for us. Right, so we're going to take antiderivatives. And what's going to happen is we're going to come out across functions that have very complicated antiderivatives. And so we're going to learn some rules to figure out, like the integral equivalent of the quotient rule and chain rule. Okay?
So what was the thing, how do you find the antiderivative we learned about?
Right, so the power rule for antiderivatives is that if you start with x to the n, your antiderivative is x to the n plus 1 over n plus 1. Okay? So in this case, if our function is x to the third, our antiderivative will be x to the fourth over 4. Okay? The notation that you use for evaluating that is this little bracket thing with the, pinpoints there.
Wait, what?
Yeah, this is the problem. So the antiderivative of
And then
x
you
to the
just
third
plug
is
in
x to
one
the
and
fourth
negative
over
two.
4. And so we're going to plug in 1 first.
1.
So that's going to be 1/4 minus what you get when you plug in -2. So -2 to the fourth is 16. So that would be minus 16 over 4. So our answer would be -15 over 4. Okay? So that's how you evaluate any.
So that's the area under the curve.
That would be the area under the curve, y equals x cubed. So it's this guy right here. And we're going from -2 to 1. So the stuff underneath the curve is greater than the stuff above the curve. And so that's why the answer comes out to be negative.
Deal with that.
Yeah, very simple.
Really confused.
When you plug
I
in
feel a
like
lot better.
-2, that's just one x coordinate, that's not the
I
entire.
was not feeling good.
Obviously, you were not paying attention when I read this part right here. It says, it's very surprising that the integral from a to b of f of x dx, which was defined by a complicated procedure involving all of values, can be found by knowing the values of f of x at only 2 points, a and b. It's surprising, isn't it? That's what you're pointing out right now. You're saying, wait, that doesn't make any sense. How can we find the whole area only using these two things? But I'm telling you, it's so crazy, it just might work. That actually will work. Okay?
So wait.
Or actually,
Well, I think it was Leibniz and Newton and
No, Mike.
Was there a race?
I don't know.
Who's
there
gonna
any
go
proof
first?
of this?
So you just plug,
Was there any what? Proof of this and
Yeah.
so you just took the antiderivative.
Yeah, exactly.
The integral of
Velocity
current
and distance and acceleration, there's your proof. Yeah,
You just took the antiderivative and plug.
plug the top number in and then plug the bottom number in and then subtract.
That's all.
That's it, yep. Okay, so we did this problem 2 weeks ago at the very beginning. This is our introduction that we did. It says find the area under the parabola y equals x squared from 0 to 1. And so you can write that as what's the integral from 0 to 1 of x squared dx? We already know the answer. 1/3, right. So we did this a lot of different ways. This is when we did the 3,000 rectangles. And we found out that as we got more and more rectangles, it was getting closer and closer to 0.3 repeating. Then we did the crazy limit of an infinite number of rectangles with the, the formula and all that kind of stuff.
remember we
And-
went to the really big number and then.
yeah, right. And now we're going to confirm that with our antiderivative. So what's the antiderivative of x squared?
X cubed over 3.
x cubed over 3, and then I'm going to go from 1 to 0. So if I plug 1 into there, I get 1/3. Minus, if I plug 0 into there, I get 0/3. And so the answer is 1/3. Okay? That works out. What is this?
No, I like it.
This works for any equation.
Yeah.
It's like any crazy curve.
Okay.
Remember that one day when we were going crazy about that equation, like if it worked for every equation?
Yeah.
It's over
Yeah.
6.
Yeah, it's always funny to teach this because you know the punchlines of it. Okay, what's the area under the cosine curve from 0 to b, where b is in between 0 and pi over 2?
What's the original question?
Really, for the cosine curve, awkward way of saying what is the integral from 0 to pi over 2 of cosine of x dx. So the antiderivative of cosine is
Negative sign.
positive sign, and the derivative of sine is cosine, so they switch around. So the antiderivative of sine is now negative cosine, and the antiderivative of cosine is regular old sine. So we go from pi over 2 to 0. Okay, so the sine of pi over 2 is no 1, top of the arc, right?
Yeah.
So sine of pi over 2 minus sine of 0, and that equals 1.
That's
Sine of 0 is 0.
That's how you show it.
Yep, that's how you would show it.
This is awesome.
Way easier.
I'm so tired.
Okay. All right. Then we also just have to be careful. So what's wrong with the following calculation? It says we're going to do the integral from -1 to 3 of 1 over x squared
The
dx.
antiderivative.
So they did the antiderivative. They said, okay, 1 over x squared is like x to the -2, right? So if we use our n plus 1 rule, -2 plus 1 is -1 over -1. So the antiderivative is correct. All right? And then they plugged in 3, and 3 to the -1, you would put it on the right 1 over 3, so that would be -1/3, and then they plugged in -1, and got 1, and subtracted those and got -4/3. Okay? So all the math looks correct, right? The problem with this is, if you go back to the magic thing that we wrote down, it needs to be a continuous function on that interval. And what's wrong with that picture here? Not continuous where?
X.
At 0, right. And since 0 is in between -1 and 3, we can't use this method to figure that out, okay? So we could do the integral of this from 1 to 3, or we could go -3 to -1 or something like that, but we can't cross through the 0 point. You say undefined, no solution, don't know. Think about the graph of 1 over x squared. Hi, Jennifer. It's possible.
Are your keys purple?
You made
I picked them, they were in Miss B's room, I think they should go office. I'm next to your one.
Oh my gosh! You'll be fine. It's all gonna work out. If you go from -1 to 3, you've got these crazy asymptotes going on here, and so there's no way you can find the area, right? Because these go forever. Right. Yeah, which is undefined. Definitely not -4/3. Okay. All right. So wrap it up with this. This could just bring tears to your eyes. The fundamental theorem of calculus is unquestionably the most important theorem in calculus, and indeed, it ranks as one of the greatest accomplishments of the human mind. Okay? Before it was discovered, from the time of Eudoxus and Archimedes to the time of Galileo and Fermat, problems of finding areas, volumes, and lengths of curves were so difficult that only a genius could meet the challenge. But now, armed with the systematic method that Newton and Leibniz fashioned out of the fundamental theorem, we will see in the chapters to come that these challenging problems are accessible to all of us. I'm surprised you guys didn't all just spontaneously jump out of your
The book
seats.
just dissed us.
The book just dissed you? Yeah, you're not a genius. Okay? But you
No,
can
right,
do
we are geniuses.
Is the plural of genius
genii, geniuses.
It's all
or genies?
We just have to have I.
Everything.
Movie guys.
Don't forget to grab the mic tonight.
Yeah.
Yeah, that's right now. How many is that? What's 34 minutes?
15 plus 1 is 16.
Are you in the bathroom?
Yep. Okay, so Raina, if you want to go to